In 1973, an Israeli geologist drilled nearly 700 meters beneath the Negev Desert and discovered an entire sea. It had been trapped there for hundreds of thousands of years. It seemed Israel had finally solved its water shortage. But the water was undrinkable. It couldn't be used to irrigate crops either, so they did something that sounded completely insane. They brought tropical fish from Australia and released them into the underground sea beneath the desert. And that was only the beginning. To understand what happened in the Negev, you need to understand one thing about water. Israel is a country the size of New Jersey, where more than 60% of the territory is desert. It has no major rivers, no natural freshwater lakes. Annual rainfall in the Negev is 25 millimeters. That is 40 times less than New York, which is why the British mandatory government officially classified the south of the country as legally uninhabitable. But beneath that classification lay a mistake. It concerned what to look for. The problem was that this water turned out to be completely useless for everything people normally do with water. First, it was hot. Geothermal heat kept it at a constant 37 to 40 degrees Celsius. Second, it was brackish, 20 times less salty than seawater, but salty enough to destroy wheat and most common crops within weeks. Third, it couldn't be drunk. It left a mineral taste in the mouth and slowly damaged kidneys with regular consumption. The engineers looking at those boreholes in the 1970s saw an expensive mistake. The money was spent, the water existed, but it was useless. Most ordinary countries would have closed the wells and gone looking for other solutions. But Israel was already building one of the most complex water supply systems in the world. It was desalinating seawater and recycling sewage back into irrigation water at scales that seemed impossible at the time. The people building that infrastructure had a habit of looking at unusable resources and asking, unusable for what? That was the question Samuel Appelbaum asked. He headed the Blaustein Institutes for Desert Research's Center for Desert Aquaculture at Ben-Gurion University of the Negev. Throughout the 1980s, he and his team systematically studied the Negev's groundwater and kept returning to one question. What animal already lives in warm, slightly brackish water and thrives there? The answer was found not in Israel. It was found 10,000 kilometers away. Barramundi, Lattes calcarifer, a tropical fish from the river deltas of Australia and Southeast Asia. It is born in estuaries where fresh water mixes with salt water. It doesn't merely tolerate heat, it requires it. The optimal growth temperature for Barramundi is 26 to 32 degrees. Below 15 degrees, the fish's heart stops. It literally dies from the cold. When Appelbaum placed that data alongside the characteristics of the Nubian water, he saw what nobody before him had seen. Every defect of the Negev groundwater was an advantage for Barramundi. Temperature of 37 to 40 degrees. For a heat-loving fish, free heating, year-round, non-stop, without electricity bills. While farms in Europe and North America shut down in winter or spend millions heating water, the Negev Desert gives Barramundi eternal summer. Salt? At the right concentration, it suppresses the development of parasites and fungal infections. For fish raised in fresh water, disease is the main source of losses. In the brackish water of the Negev, the fish grew cleaner. Appelbaum would later describe it this way. He hadn't found a solution, he had found a match. Millions of years of evolution had already solved the problem for him. All he had to do was bring two elements together. Alongside Barramundi, the researchers decided to raise Nile tilapia and sea bass, also tropical species, also tolerant of warm, brackish water. 3 species, 1 aquifer. But between the laboratory and a pond in the desert lay a chasm. The years ahead would show just how deep it was. In 1979, the first experimental ponds in the Arava Valley, the far south of Israel, where the desert is harsher than in the central Negev. Appelbaum and his colleagues pump in geothermal water and introduce the first fish. The results exceed expectations in the areas where he had anticipated problems. The fish grows. In conditions of constant warmth and optimal salinity, Barramundi gains weight faster than in its natural habitat. In Australia or Thailand, fish grow in summer and slow in winter. In the Negev Desert, there is no winter. FAO farms recorded that in some ponds, the yield was 35 times higher than in the subtropics. But simultaneously, a problem emerges that nobody had anticipated. 1 million fish in enclosed ponds produce enormous quantities of waste. Ammonia, nitrogen, phosphorus. Ammonia is especially dangerous. It corrodes the gills and kills fish within hours if the concentration exceeds safe limits. In the open ocean, waste dissolves in billions of cubic meters of water. In a concrete pond 250 square meters in size, it accumulates rapidly. The conventional solution is to drain the water and replace it with fresh. But in the desert, water is currency. You can't simply dump it. And building industrial filtration systems for every pond destroys the entire economics of the project. 5 pilot farms established in the 1980s and early 1990s hit this wall one after another. Some close due to poor management, some due to financial difficulties. The most painful failure involves tilapia. It becomes the backbone of the first farms, but in the mid-1990s, its price in Israel collapses. The market is saturated with cheap imports. Farms that cannot pivot to higher-value fish disappear. Of 5 pilot projects, only 2 reach full commercial scale. But it is at precisely this moment that researchers at Ben Gurion University find what changes the entire logic of the system. Appelbaum and his colleagues look at the dirty fish water, saturated with ammonia, nitrogen, and phosphorus, and realize they are not looking at waste. They are looking at fertilizer. The chemical composition of fish effluent almost perfectly matches what plants need. Nitrogen for leaf and stem growth, phosphorus for root systems and fruit. In conventional agriculture, these elements are applied to soil as synthetic fertilizers, which cost money and acidify the soil with extended use. Here, they are already dissolved in water that needs somewhere to go anyway. This is how the dual system is born, the key mechanism that will make desert aquaculture profitable. Water comes up from the borehole at 37 degrees and flows into the fish ponds. The fish use the heat and enrich the water with organic waste. The cooled, nitrogen-rich water flows directly through pipes to the fields. At the Ram farm in the Negev, this system serves 120 hectares of olive trees year-round. In winter, they need 10 cubic meters per hour. In summer, up to 100. The olives absorb the nutrients. The soil acts as a natural biofilter. The water gradually purifies and percolates downward, returning to the aquifer. 2 resources instead of 1. 1 pumping operation instead of 2. But the biggest surprise came from agronomy. Farmers expected olives on fish water to grow worse than on freshwater with synthetic fertilizers. Instead, studies showed the yields were identical, without any chemical inputs. Fish waste completely replaced an entire industry of synthetic fertilizers, not partially, but entirely. The waste that needed somewhere to go turned out to be the equivalent of what is normally purchased and trucked in by the tank load. Agronomists had waited for confirmation, but the results were stronger than the forecasts. Olive trees irrigated with fish water produced higher yields than plots watered with fresh water and synthetic fertilizers. Organic nitrogen is released slowly, at exactly the rate roots need it. Some agronomists recorded that the salt in the water didn't harm the trees, but instead caused the fruit to concentrate sugar under mild salinity stress, improving olive quality. The fish farm and the olive grove became a single organism. The fish fed the trees cleaned the water, and then 1992. Kibbutz Mashabasadeh, 90 kilometers south of Beersheba, almost on the Egyptian border. The name of the kibbutz translates as field resources. Founded in 1947 by Palmach veterans, Israel's elite fighting unit, the people who built this place were accustomed to solving problems for which solutions didn't yet exist. Now they are building a concrete reservoir 3 hectares in size and a row of covered ponds at 250 square meters each. They order Barramundi fingerlings from Australia and Thailand. They pump geothermal water from the borehole. The first months are pure uncertainty. Nobody in the world has done this at industrial scale before. Every week brings new decisions. What fish density is optimal per pond? How often to change the water? How to feed fish under conditions of constant heat? Water arrives at 37 degrees, and if the fish suffocate from ammonia, no natural current will dilute the concentration. Only people and technology can. But the fish grow. Fish farmer Amit Ziv and his team in wetsuits drag nets twice a week. 1.5 tons of barramundi in a single haul, among sand and rock, under a burning sun, in a place where rain falls once every few months. Kibbutz Mashabasadeh becomes the first and only of its kind, the only kibbutz in Israel raising Australian barramundi. And the profit it begins to generate changes the calculations for the entire industry. Fish that commands a high market price, plus water that costs almost nothing, plus fertilizer that goes free to the olive groves. This is a formula that holds. But the challenge isn't over, it only gets more complex. A few years after the ponds are launched, a problem emerges that fit none of the original spreadsheets. Barramundi is a cannibal. In an enclosed pond with high fish density, larger individuals eat smaller ones. This is normal behavior in the wild, where fish are spread across large areas. In a concrete pond, 250 square meters in size, it becomes a production disaster. You stock 1,000 fingerlings and a few weeks later find a third fewer. Not because they died, but because they ate each other. The solution is constant size sorting. Fish are regularly netted, weighed, and redistributed between ponds by group. Smaller ones separate, larger ones separate. It is manual labor, stress for the fish, and an operation that never ends. Simultaneously, the farms face an oxygen problem. At 37 degrees, the solubility of oxygen in water drops. Fish suffocate faster than in cold water. Water must be constantly aerated, equipment that breaks down, and a single aeration failure of a few hours can cost an entire crop. And there is a question that Applebaum never concealed. The Nubian aquifer is not infinite. It does not recharge, or recharges so slowly that on a human timescale it amounts to the same thing. By Applebaum's own estimates, the groundwater reserves of the Negev will last approximately 200 years. Then this water will run out. Desert aquaculture doesn't solve the water deficit problem. It buys time, but that time is not empty. Those who survived the first wave endured not because they had more money or luck. They endured because they found the right product for the right market. Barramundi is not a cheap fish. In Israel and in Europe, it sells as a premium product, fresh, raised without antibiotics, without heavy metals, without the microplastics that inevitably accumulate in fish caught in the open ocean. These characteristics, not its exotic origin, made it commercially viable. Today, aquatech fisheries in the Negev covers 3.5 hectares and produces 2,000 tons of barramundi per year. Water arrives at 37 degrees, passes through a closed cycle, and exits to the olive groves. All electricity comes from solar panels installed above the ponds. Fish is sold fresh across Israel and exported to France, Germany, and the United Kingdom. Kibbutz Mashabasadeh produces 200 tons per year. More than 10 super-intensive fish farms have been built across the Negev and the Arava Valley, but the most important thing to grow out of the desert was technology. The engineers of Aquamayoff Aquaculture Technologies began their work in the Negev. The closed recirculating aquaculture system technology they refined in the desert, where mistakes are fatal and water is never surplus, became the foundation for farms on 5 continents. Today, Aquamayoff builds and operates projects in Poland, Japan, Russia, Canada, Chile, Indonesia, Malaysia, and Belize. The largest of them is a facility near Mount Fuji in Japan, designed to produce 10,000 tons of salmon per year in closed land-based conditions. No ocean, no trawls, no coastal water pollution. Applebaum has calculated that desert aquaculture worldwide produces over 30 million tons of fish and seafood per year. It is an industry worth more than $40 billion. Techniques learned in the Negev are now being applied in Kenya, Tanzania, and Namibia. Other arid regions where underground aquifers are waiting for someone to ask the right question. Ben-Gurion University receives graduate students from Central Asia, Africa, and the Middle East, countries where drought is becoming the norm rather than the exception. They come to learn what began with one pond at Kibbutz Mashabesad in 1992. But a question remains open. Barramundi requires feed, and feed consists of fish meal and fish oil, meaning wild fish caught in the ocean. Growing 1 ton of barramundi requires a certain quantity of wild catch input. A closed-cycle farm on land doesn't remove pressure from the ocean entirely, but it redistributes it. But there is a nuance that changes the picture. Barramundi is one of the most efficient species in aquaculture by feed conversion ratio. To grow 1 kilogram of barramundi requires 1.2 to 1.5 kilograms of feed. By comparison, salmon requires 1.5 to 2. Beef, more than 6. And unlike salmon, barramundi can grow on a diet with minimal fish meal content, partly on plant protein. Some producers have already achieved a fish-in, fish-out ratio below 1, meaning the farmed barramundi weighs more than the wild fish consumed to feed it. This is rare in aquaculture. The Negev system is not perfect, but it is considerably more honest than what happens in the open ocean, where a single trawl in one night can destroy decades of seabed recovery. The question is not whether it has flaws. The question is, compared to what? And there is one more detail. The figure of 1 million fish is an image, not an accounting unit. The actual industry counts in tons per year. The scale is impressive, but it doesn't eliminate the system's fragility. One disease outbreak in an enclosed pond, one aeration failure, one management decision, and years of work disappear in days. Those who survived in the Negev know this better than anyone. In 2026, more than 40% of Earth's land surface is classified as arid or semi-arid. By 2050, that figure is projected to grow. We are talking about billions of people living where rainfall is decreasing, rivers are shrinking, and conventional agriculture is managing less and less. Israel found its answer in the 1970s, not because it was a genius, but because it had no other choice. It drilled 700 meters into sandstone and found a sea that was good for nothing, and then found the one thing on the planet for which it was a perfect fit. What looked like a joke in the 1980s, fish in the desert, is today a blueprint for countries only beginning to grasp the scale of their water crisis. We knew there was a need, and that this could meet it, Applebaum said. The need hasn't gone anywhere. It has only grown.